Okay, welcome ladies and gentlemen to section 2.3 dealing with polynomial functions, looking at some of the stuff you might remember from last year or from previous classes. They're kind of important things to think about when we look at polynomials, and we're just going to go ahead and jump right in. So first of all, we like to see what is the general form for a polynomial function. And general form or standard form is going to look like this. Now that looks very, very daunting and looks very scary, but it's really not. A sub n times x to the n is the leading term. That's the term with the largest coefficient. And you notice how, or sorry, the largest exponent. And you notice how the exponents decrease by 1. It would be something along the lines of 3x squared minus 4x plus 7. Notice it goes from exponent of 2, exponent of 1, down to an exponent of 0, where this last term here has an x to the 0 power. This is x to the first power here. And it doesn't matter how big we make this thing. We could add a 4x to the third here. We can have a 6x to the fourth. Just notice that standard form decreases the exponents from left to right. So a sub 0 is called the constant term. In the case of the polynomial up here, the constant term is 7. The leading term is 6x to the fourth. The leading coefficient is 6, and the degree is 4. Now, one of the things that comes up, and one of the very large things that comes up in polynomial functions, is the use of x-intercepts. X-intercepts have different names. They're called zeros, they're called roots of the function, or they're solutions. They're solutions to the equation where this equals to 0. That's why they're called zeros also. So we kind of know a lot about quadratic functions, so let's move a little bit forward into cubic functions or cubic polynomials. Now, a cubic polynomial is one that we have f of x is equal to ax cubed plus bx squared, if we're looking at standard form, plus cx plus d. And what we're going to look at is the possible outcomes of these types of functions. So the first thing is the possible end behaviors, meaning as x goes to infinity and as x goes to negative infinity, what happens to the y values? Now you might remember from last year, because it's a negative exponent, they're going to go in opposite directions. So I know it could do this and this, or it could do this and this. This being the end behaviors where they just go to infinity and negative infinity here. The shapes. There's a couple different ways this shape is going to look. Now this could go in the same direction I'm going to draw it or in the opposite direction, but it could look like this, or it could even look like this. A little bit more exaggerated bumps there. Both of these are cubic functions, or are possibly cubic functions. For the number of zeros, you notice here, this is 1, means I could have 1. I could have 1, 0. That's a possibility. Something like just the function, oops, where am I going here? Just like the function x cubed. That has 1, 0. Or I could have this where it's got, or if I think about them as x-intercepts, I could have a possibility of 3. I could even have 2. And 2 is going to look like this, where it kind of comes up and it bounces off the x-axis. You might remember some of this stuff from last year, like I said. So I could have 1, 2, or 3 x-intercepts. But the most I can have is 3. But I can't have 0. There's no way for me to get 0 x-intercept for a cubic function because of the way the graph has to be shaped. And there's going to be a theorem for this here in a moment. And the number of y-intercepts, that's always 1. You can only ever have one y-intercept. You can't have more than one. And you can't have 0 either. There's no possible way for these to have 0 y-intercepts. And notice here. So notice I could have up to 3. So x is between 0 and 3. I can have up to 3. And for the number of extrema, look at these two graphs that I drew. I have that one and that one. I have that one and that one. It means that I can have 2. And if you try to draw a whole bunch of cubic functions, you'll start noticing I could have x equals 0, or sorry, not x equals 0. I could have 0 or 2. Try to draw a cubic function where you only have one minimum or one maximum. It's just not going to happen. I can have 0 like this function here, or I could have 2 like these two functions here. All right, it's enough for cubic. These are just kind of things that you should be thinking about as you're going through looking at the cubic functions. What about a quartic? Quartic is just a 4th power polynomial. So we have f of x is equal to ax to the 4th plus bx to the 3rd plus cx squared plus dx plus e, if you want to go out that far. And again, the possible end behaviors. If you recall, because it's a even power, it's going to go up, up, or it could go down, down. And I didn't mention this before, but this is for a is bigger than 0, and this is for a less than 0. If you want to go back and add that to the cubic functions, this is for a bigger than 0, and this is for a less than 0. For the possible shapes, now quartics have a lot of possible shapes here. We could look like this. That's pretty interesting because it looks like a quadratic. You're right, because cubics or quartics can look like quadratics because they're very similar functions. We could have something that does this. We could make it look like a W. We could make it bounce off the x-axis, which is going to come in handy. But that's actually about it. There's really not much else we can do. I can make it so one is here and the other one is way down here. But quite honestly, that's about all the more interesting they get. But notice this, the number of zeros. I can actually draw a graph of a quartic that has no x-intercepts. I could draw a graph, if I looked at this U-shaped one, I could have it where there's one x-intercept. This one bounces off the x-axis, and I can have 2 x-intercepts. I could also make one that has 3 x-intercepts if I just try it a little bit harder. If I go like this, there's 2, and there's a third one. I'd have 3 x-intercepts. And I could have one that's 4, like this one right here. But again, you can only have a single y-intercept. You couldn't be a function if you had more. And again, look at this, the number of extrema. I could have 1. I could have 3. Notice here I got 3. But look at all these examples. I can't have 2, and I can't have 4. So I can have 3 extrema in this on quartic functions. So let's take a look at a quick theorem that comes from this. This is actually a very important theorem. This says that a polynomial function that has degree n can have at most n minus 1 local extrema and at most n zeros. So if I gave you a cubic function, that means I could have at most 2 extrema and 3 zeros. If I gave you a x to the 6th power, that means I could have at most 5 extrema and 6 zeros. And you could try for eternity to try to find an exception to this theorem, but it wouldn't be the case. And if that was the case, you wouldn't have a theorem. All right, let's look at how we would sketch these graphs. In order to sketch graphs, that just means find your key pieces of information. I know it's a cubic, and I know it's positive, and therefore it's going to go like this for an end behavior. And I can go, okay, well, I can factor out an x, and I get x squared minus x minus 6. Well, that factors even farther. And it looks like this. Well, that means I have x-intercepts of 0, of 3, and of -2. And since it's a cubic that goes down over here and up over here, I have to be able to connect my dots in such a way that I get my cubic to go like that, and that is a sketch of the graph. There's no way for you to actually know the mins and the maxes here. Not from what we know how to do. So first you're going to factor. You're going to plot your zeros, just as I just did. And then you're going to sketch using your end behavior, just as I just did. I knew since it was a positive cubic, it had to go down into quadrant 3 and up into quadrant 1. But what about this thing called multiplicity? You might remember this word from Algebra 2. This is what happens when I have a repeated 0. Something like this. These are really good, fun equations to try to graph. This tells me I have zeros at -1 and at 3. But then I need to know what is the degree? Well, this is an x squared and this is an x to the 3rd, which means I get x to the 5th. Well, that means it's a positive because it's x and x. Those are both positive. So it's a positive x to the 5th, which means it's this type of end behavior, down on the left, up on the right. Okay, so I know that. I can find my y-intercept. It would be 1 squared times -3 to the 3rd. -3 to the 3rd is -27 times 1, so it's down here at -27. But what does it mean to have multiplicity graphically? Well, it means you're going to see this on the next slide here, this 2 means to bounce. And this 3 means to squiggle. Squiggle through. Okay, so if I start down here, I'm going to come up to this -1. I'm going to bounce down through -27, and then I'm going to come up and do a little squiggle through the +3, and that's kind of what this function would look like going through this function, or going through those zeros. So -1 is 0 of multiplicity 2, and 3 has a 0 of multiplicity 3. Usually when you're writing this on your homeworks and stuff, you would say -1 mult 2 and 3 mult 3, multiplicity 3. So this is what I was mentioning on that last page. If you have an odd multiplicity, it crosses the x-axis, and it actually crosses like a cubic would. It would cross like this with this little squiggle through, like I did on that last problem. And f of x, the function changes sign, so it goes from negative to positive or positive to negative. And if it has an even multiplicity, so like it's squared or cubed or 4th power, 6th power, that sort of stuff, then it does not cross the x-axis, it does not change signs, but it actually bounces like that last problem I had there. It would come up here and it would bounce and go back this direction, or bounce going upwards. And you can actually create equations from graphs. If I gave you this graph that bounced here and bounced there, and this was supposed to be a -2, and this was supposed to be a 3, I could say a possible equation for this would be x plus 2 squared times x minus 3 squared. That would be a quartic, so it would go up, up. -2 bounces, plus 3 bounces. And let's just say that this was actually, let's see, 9 and 4 is 36. Let's say this was an 18. Well, my y-intercept should be 36 by plugging in 0, but it's 18, so I got to cut the whole equation in half. That might be handy on maybe an SAT test or something like that. Could be. But who knows? Never know exactly what's going to be on an SAT. Okay, hey, that's it. I kind of like this quote here. Some people forget that. They use Bob as much as they want, and then they forget that they actually have to know what they're doing when it comes to test days. Okay, I will see you guys tomorrow. Have a good evening.